Next, we're going to talk about your series and parallel circuits itself. So your series circuit, you just need to remember, right? All you need to do is take your finger, and we always start at the positive end. If you can do one single path without lifting up your finger, this is what we call a series circuit. So basically, you just have one loop, right? Or you can say one loop or one pathway itself. And then for a parallel itself, if you try to take your finger and you trace, you notice that this is only for one loop, this is for two loops, and this is for three loops, right? So there's actually three loops. So this is basically two or more loops. All right. Now, you cannot take your finger and you basically have trace around. Now, if you overlap, kind of like a game, right? If you overlap basically, you lose. All right. So you can only take one path. You can only take two paths. You can only take three paths. You cannot basically overlap the current itself. They are one way only. All right. So you can just imagine that. So just picture yourself. If you are the electric charges inside your circuit, basically this is the path that you take, right? You'll face obstacle number one. You'll face obstacle number two. You'll face obstacle number three, and then you go back to the end. So in total, your total resistance that you face is actually the sum of the three of them, 1, 2, and 3. So if all of them are, for example, this is 3 ohms, 3 ohms, and 3 ohms, right? So all you need to do is 3 plus 3 plus 3. In total, you face 9 ohms of resistance. So your resistance is actually very, very big because all of them add up together. So you can see your current that flows will be like this, right? So similarly, for your parallel circuit itself, your current will flow like this. You'll notice the current will actually split into three parts. So basically, the red color current will split into the blue, green, and the purple parts over here. So same thing when you come over here, your purple, green, blue, purple, you combine back again into your red color, and they'll come back over here. So what I mean by this is basically this is your total current. You have current 1, you have current 2, you have current number 3. So basically, you can just imagine as a race or an obstacle course, right? You actually have three paths that you can choose. So because you have three paths that you can choose, it's actually going to be easier. So over here, we don't actually use the formula down here very, very often. Okay, so we don't use this one, not very often. We don't use this, we'll use this one. So total resistance or your effective resistance, right? We're going to be 1 over R1, R2, and R3. So basically, you can see that we have uh, three fractions, right? Each fraction represents one branch. So you can see we have three paths, right? So because each path you have will have one fraction each. So you have two paths, you have two fractions, three paths, three fractions, and so on and so forth. All right, so do take note about this one. So for your effective resistance over here, if you put in series, you'll always be bigger. So what I mean by this is if you add resistor in series, total resistance will increase. Okay, so if you do the opposite, if I remove the resistor in series, my total resistance will decrease. All right, so if you so just need to remember, series you add become bigger. Parallel, on the other hand, if you add, it will actually become smaller. So if you add a resistor in parallel, what happens is that your total resistance will actually decrease instead. Okay, so you can see over here the line here, your total resistance. Now you see this word effective resistance, right? This is actually the same as the word total. They mean the same thing. Okay, so your effective resistance is down here, so you can see over here. Now, let's take a look on the left. Now, this is what we call a complex circuit itself. Why? Because if you take your finger and you trace, you'll notice that I have path number 1 here, and then I also have path number 2 over here. But you'll notice that in both of these paths itself, what happens is, so I'm just going to highlight it to show you how the current flows, okay? So you'll notice that over here, your current flows here, and then at this point, your current will actually split into two parts. You will split into here and here respectively. So what happens is you have this point and you have this point. So this current will flow here, this current will flow here, and then what happens, they'll actually merge back over here. So at this point, you become here again. Now for your ammeter and voltmeter, basically we'll just ignore them. Don't pretend that there's no current flowing through them at all. Just ignore that they are not there. So if you notice over here, if this is the case, how do I find my total resistance? Because now I look like I have one series here and I have one parallel here, right? That's correct. There is actually a series and this is a parallel. Because you notice this R is in series with this parallel over here. So how do we solve this problem? How do we find your total resistance? First things first, we try to simplify our diagram as much as we can. So we just zoom into this parallel part over here. So for parallel, right, if you want to find the effective resistance of the parallel, what do? Parallel, right, we're going to use the weird formula, 1/2, 1/6. We're going to end up with 1.5 ohms, all right? So which means that this entire parallel part, I can replace it as a 1.5. This guy here is my parallel, all right? Well, the rest of the whole entire setup is still the same itself. So now, if you want to find your total resistance, what do? All we need to do now, because now it's a series circuit, one loop, right? It is just R plus 1.5 ohms. You see that? So as much as you can, if you ever face a weird question, remember, the first thing you do when you see a brand new circuit is actually just to take your finger and you trace what is the path that you take. Okay, now this one. You want to trace the path you take. There is two paths, and if you notice, this guy is repeated. So because R is repeated, it's actually in series with the rest. So if you can actually grab some highlighter, but I don't recommend that unless you're using the friction one, because if you highlight it wrongly, you are kind of screwed because you cannot erase the highlighters, right? So just take note about this, right? So let's do this example together. So same thing, when you see a circuit, first thing you ask yourself, oh, this guy is series. Same thing, this guy is in parallel. Right? Then this one is question mark. So first things first, if you want to find total R, or in this case, effective R, right? I'm just going to use the word from the question. Series, I'll just add them up. 4 ohms. Because why? Because if I want to take my current and flow through, I'll just flow through in the same path. So I'll just, my electric charges are flowing in the same direction. They are all moving through two of your resistors. Okay? Then for a parallel itself, parallel formula, we need to use the weird formula, 1/3, 1/3, 1/3. Okay? So you end up with 1 ohms over here. Because why? My current will split into what path 1? Path 1, path 2, and path 3. So because I have 3 choices to make, I can choose which path I want to do. So because of this, I actually have less resistance because I now have the ability to choose which one do I want to go. So your total current will split into path 1, path 2, path 3. So you can choose. So you can see that your resistance that is blocking you is going to be smaller because now you can choose which path you want to go. Now, for this one over here, it looks very complicated. Right? It's like, how come my current got this, got that? Very complicated. So let's try to make things easier first. Now, ask yourself this part. What is this? Series or parallel? This is actually in series, right? So you can just imagine I have my 4 ohms and my 4 ohms here. So on top, 2 ohms and 2 ohms. These two guys are in series. So I can take 2 plus 2, you end up with 4 ohms over here. All right? Now, then you look over here in your parallel parts. You have 4 ohms and you have 4 ohms, right? So what you can do is, is that this 4 ohms is 1 over 1 over 4, 1 over 4, close bracket, you end up with 2 ohms. So this one you can see on top here, it is effective R for the series part only, 2 plus 2, and I have 4 ohms. Right? So this on the left, sorry, on the right, this part can be replaced by your 2 ohms. Then once you reach this point, it's just a pure series circuit. So 4 plus 2, you end up with 6 ohms. Okay, so always try to simplify it to the point where it's basically idiot proof. It's just a simple series or simple parallel itself. Try not to do it one shot because sometimes it gets very, very confusing if you do a very, very big equation. So do take note about this. Right? Now, this one is not resistance of the conductor, it is of the wire itself. Most of the time, it is wire. Okay, but conductor is technically true as well. So, not really erasing, it's more like they are referring to wires. So, resistance of a wire increases when your length increases. So, you can just imagine, now I have L. Okay, your length L. And you have an area A here. Okay, now basically I have a certain resistance here. Okay, I have R. So if I have double the length but the same A, okay, but now I have 2L. What happens to resistance? So just remember, resistance is the obstacle that's blocking my current from flowing, right? So if I have 2 times the resistance, if I have 2 times the length, I will actually end up with 2 times the resistance. Because why? Because I will need to travel an additional distance. So it's kind of like running a marathon itself. Which one is easier? Which one is harder? I ask you to run 1.6. Wow, very difficult. Then I ask you run 2.4. Sure, I want to do 1.6. Right? Because your 2.4 is longer and you therefore will have more resistance that you have. So obviously we're going to take the easier path. We will choose 1.6 kilometers to run instead. So similarly, instead of that, if I have a much bigger A, 2A, and this is still L. Now, you can just imagine all my electrons are basically traveling through the wire, right? So you can just imagine all of them are squeezing inside that small little path to take. Okay, so you have a much bigger area itself. We don't need to squeeze. And if you don't need to squeeze, you actually will have less resistance. So in this case, your area and your length, they are actually your area and your resistance are inversely proportional. So if you increase A, you will actually do the opposite for your resistance. Okay? So do take note. Now, this is area, which means the question can make your life more difficult if they give you diameter or radius itself. Because this is a circle, so we need to use pi r square. So you need to be more careful about all of this. Okay? But basically, you can see length increase, resistance increase. All right, maybe I'll just write it down here. As length increase, resistance increase. Okay, and as your area increase, you have the opposite effect, resistance decrease. Okay, so do take note about this. And then all of these symbols that you see down here, these are your circuit symbols, which means that instead of drawing a 3D diagram of all our devices, like a battery and whatnot, we will use this to represent what is the components itself. So this is an open switch, and what's so special about open switch is there's no current. Okay, because don't forget, current is the rate of flow of electric charges. So if my current cannot flow, you don't have current. So if you have a closed switch, your current can flow easily. So it's okay. Light bulbs are drawn like this. Your resistor. So this one in particular is what we call a fixed resistor. So you guess why it's called a fixed resistor? Is because it has a fixed resistance. which means that the resistance of this guy is a fixed number. You cannot increase or you cannot decrease. It's going to be a fixed number itself, like 15 ohms or whatsoever. All right. Now, below your ammeter, voltmeter, those are straightforward. This is an electric cell. This is singular. Okay. Then on the other hand, if you have a group of cells, this is what we. So your battery itself is always a group of cells. It's a bunch of cells. So it's like a group of person. A battery is just a group of cells. All right. And then you have what we call a variable resistor. It's also called a rheostat. Okay. So as the name suggests, you actually have changeable resistance, which means this device, I can actually change the resistance. I can put like 2 ohms. I can change it to 15 ohms. I can change it to 30 ohms as much as I want. Okay. So this is your devices. Now, this is basically a special case. So this one is a special case, special situation or scenario. Okay, so you must first, number one, I have a path for current to flow through and there is no resistance. R is 0 ohms. Okay, so what happens is when you have a short circuit, current will be, this is what we call a short circuit. Current is very high, can be dangerous itself. Okay, and why is it traumatic? Because no current will flow through your device. So for example, let's close all the switch. Okay, I'm going to close all the switch. Close the switch, close the switch, close the switch. So first things first is current will flow like this, and you see this black dot itself. Now, usually when you see this black dot, right, this is what we usually is a sign, might be parallel. Okay, so you can see current will flow through here, and current will flow through here. So in the end, you have this part. So you can see this part. When you reach this point, you have yellow and you have blue. Okay, then you continue on with oops. Then you continue with this part. Right? After it merge back again. Now, if your switch here is closed, the problem is this guy. Resistance is 0 ohms. So what happens is that all of the current here will only flow through here. There is actually no current flowing through your light bulb. So what happens here is when you have a path of 0 ohms, no current will actually flow through here. So what we can say is when switch S3 is closed, wait, is that S3? No, S1. The L1 is short-circuited. Okay. So L1 will be short-circuited. What does this mean? No current will flow through L1 and thus it will not light up. Okay. So do take note about this. Your short circuit, right, basically word 0 or the word negligible. Okay, so this is a condition for it to trigger. I spelled it wrongly. Okay. So you can see over here basically is that now you must have 0 resistance for you to be short-circuited. So you don't, so for your current, right, your current don't like just choose only one path because you can see these two are parallel, right? And you see S1 and L1, they are parallel as well. But because this guy is in particular, it is 0 ohms, then you can have short circuit. So short circuit must have if and only if you have a path of 0 resistance instead. These two got other resistance, so like other numbers like 10 and 10. So because of the non-zero resistance, it will form parallel circuits. All right. So for these two, the legend itself, you don't need to worry about this. Basically, it's something that we use quite commonly. Now, next, let's talk about your series and parallel, because previously we only talked about your resistance, right? How do we calculate total resistance? So now we need to know how do we actually find your current and your voltage respectively. So series circuit means all your components are, they only have one path to take. It's arranged in one single loop. Okay. Good thing, it's very simple to set up. Okay, and cheap. Bad thing is if a problem, all components do not work. Okay, so that is the problem with your circuit. So in your series circuit itself, if you were to just draw your current, you will notice that it is the same current throughout. So what does this mean? My total current is the same anywhere else. They are all the same. Okay. Now, whereas your voltage itself, if you see over here, you're going to flow like this. Now, your voltage, on the other hand, this is my total V, right? I'm going to use up all of my V2 versus V1 and V2. So, which means total V is the sum of V1 plus V2. Because I need to use up all of my total V in one single path. V1 and V2 are the V1, the resistor R1 and R2, they have their own resistance, right? So you can just imagine it's like climbing a mountain. You need to use up some of your energy to overcome your mountain. So because of this, we will actually use up some of your V1 and your V2 so that we use up all of the energy to go back to the battery. Okay, so first things first, this is for series circuit. So for series circuit, the number one thing we want to write is V equals IR. So if you forgot what is this formula, this is actually our bread and butter that I told you to go and memorize. Then apart from that, then we will use your three sets of formula itself. Total I is I1, is I2, total V is V1 plus V2, and your resistance just now is R1 plus R2. So if and only if this one, number one, cannot solve, then we use this. Okay, so basically it's more of an either or question. If I can use V equals IR to solve, I sure use this to solve, don't need, no problem. But do take note, there is one concern when you use V equals IR is if you use V1, I want to find V1 or VA, for example. I need to use I of A, I need to use R of A. Must be the same. Because a very common mistake is some students will use their total V, but they use RA. If you use total V, I need total I and total R. I cannot just use RA, which is just one of the two. You need to use the sum of both. You need to use total R. So let's take a look at this and see how we solve. So we know that RA is 10 ohms, okay? And we know that VA is 5 volts. So what's the IA? So IA is VA over RA. Must be same. They must all correspond. So all we need to do is 5 over 10, 0.50. Current is amperes. Okay? Now, they tell me that this is 12 volts. This is total V. Okay, total V is 12 volts. What is this? So the thing is, this is a series circuit. So first thing, ask yourself, they want to find PD of B. If you forgot what is this is VB. Okay? Potential difference is just another word for voltage. So if you want to find VB, ask yourself, do I have IB? Technically, yes. Because remember, current flowing through the circuit, series circuit is the same. So technically, yes, I do have the current, but then ask yourself, do I have RB? Do I have the resistance of resistor B? I don't. So since I cannot solve using V equals to IR, the next thing we want to do is we want to find VB, right? So let's take a look at the V formulas. Okay, so we'll use this one. So over here, what you want to first write will be total V is VA plus VB. All right, so if I want to find VB, first thing we solve is we're going to take total V minus VA. So what's total? 12 minus V8 is 5. This is 7 volts. Okay, then now you see the third part where they want to find RB, right? So if I want to find RB, I need VB, I need IB. So what's VB? I have 7 volts. What's IB? Because the current is the same in a series circuit, it will also be 0.50. So I end up with 14 ohms. Oh, and on top, my bad, it should be 7.0 volts. Okay, so you can understand, basically, right, you always remember this set of formulas. So the problem is, for electricity, every single component, your resistor, your light bulb, your lamp, all of them have their own V, their own I, their own R. So if you don't label everything clearly, because a lot of students just throw numbers, right? If you don't label all of them clearly, it's very, very, very easy to make careless mistakes, because you'll forget, is this, what am I finding? Is this a current? Is this your voltage? Is it your potential difference? Am I finding resistance? You guys might end up using the wrong units. So because of this, we try to avoid any kind of mistake. We always label everything very clearly. IA, VA, RA. Total V, total I, total R. Always make sure it's same, same, same. Once it's different, that's it. Okay? You got it wrong already. All right, so next page, we talk about your parallel circuits. So your parallel circuit, same thing, your components are arranged, 2 or more branches. So in 2 or more loops. Okay, so what's the advantage of your parallel? A fault in the component only causes that branch to not work, which means your other branches can still function properly, so that you can still have you can still do anything else. But the problem is, it's going to be more difficult and more expensive. So basically, you can just see that they are actually opposites of each other, your series and parallel. The advantage and disadvantage is actually the flip of each other. So for your current itself, so you can see over here, normally current will flow from the battery and then you go here, right? But at this point, when you see the dot, what happens is that current will split into 2 parts. You split into your blue and your green color parts. You split into yellow and blue over here. So you will split, and then at this point, they will merge back again. So if you were to just focus on either of the dots, what goes in must come out. So you can just remember your rate. So your total I, the total current is going to be the sum of I1 and I2. It's going to be the sum. What goes in must come out, okay? So you can see that your current is total I is I1 plus I2. On the other hand, your voltage itself. So my voltage, you can see this is a parallel circuit. You have branch 1, you have branch number 2, right? So just remember your total V itself, let's say is 10 volts, for example. So which means every loop, I'll use 10 volts. So in this path, I will use 10 volts. So total V is the same as V1 and V2. They're all the same. They're all going to be 10 volts in this question. Okay, so you can just imagine if I were to take my finger and I take this loop, I'll use up 10 volts to overcome this obstacle. So this obstacle here is 10 volts. Similarly, if I take my second path, I use 10 volts here, I use 10 volts to overcome this obstacle as well. It'll be like this, okay? So similarly, I will show you what do we need to take note of. So this is for parallel. Number 1, what's the first thing we do? Same thing, we still use V equals to IR. That's why I told you that this is actually your most important formula itself. Number 2, then we fill in the blanks. So total I is I1 plus I2. Total V is V1 is also V2. Now, don't forget your total resistance is that very weird formula, R1, R2. Okay? So if and only if this doesn't work, then we use these 3. So let's take a look. Now, let's see over here. The reading on emitter A2 is 4.0. So this guy, we're gonna just call it I2. I2 is 4.0. Okay, so do take note, I2 is only for the blue color path. The rest is green. All right, do take note. So now they're asking you, what is the PD, which is your voltage of the 4 ohms, right? 4 ohms is actually your V2. So they're asking you what's the V2. V2, straight away we use V equals IR. V2 is I2 and R2. So ask yourself, what's I2? 4.0. What's R2? R2 is 4. So we end up with 16 volts. Okay, so since V2 here is 16 volts, parallel, they're all going to be the same. So you ask yourself first, if you want to find battery, this is total V, right? Because when you see battery, it means total. So total V, you ask yourself, do I have total I? Do I have A0? I don't have, right? So I cannot use this. So I need to find total V. So total V is V1 and V2. So I'll write total V is V1 is equals to V2. So V2, what's V2? V2 is 16 volts. So therefore, I solve my answer. My EMF of my battery must be 16 volts because they are the same. Okay, then number 2, you want to find the ammeter reading on A1, ammeter 1, right? This is actually asking you about I1. So if I want to find I1, what's the first thing I need to do? I1 must be V1 over R1. So first yourself, what's V1? V1 on top, do you see it? It's 16 volts. And what's R1? Take a look. It is 8 ohms. So we end up with 2.0, and this is current, so M. Yes. So 2.0 amperes itself. Last but not least, what is A0 reading? A0 reading itself, A0, if you haven't noticed, this is actually your total I. So the total I, do you have total V? Yeah. Do you have total resistance? No, but we can find it, but it's a bit troublesome. You can find your parallel and then you take this and divide. We don't need to do that. So you're going to find total I down here, right? What's the formula? Total I is I1 plus I2. Do we have I1 and I2? Yes, we do. What's I1? I1 is 2.0 plus I2, 4.0. So is 6.0. Okay? So this is our answers. This is how we solve for your values over here. All right?